This is your video for your chemical bonding unit. This is the very first video. And so we're going to talk about a little bit about what chemical bonding is, some different types, and then we're going to focus on one type in particular. So first of all, we need to know that atoms don't stay as individual atoms. We learned this in the presentations before Thanksgiving break. A lot of them are not found alone in nature, and that's what the presentation said. They're always combined with something else because they're reactive. So they combine with each other to form compounds where atoms are put together. And atoms are put together in what we call a chemical bond. A chemical bond is the force that holds two atoms together. Pretty simple. In this unit, we are going to talk about three types of chemical bonds. Those three types are ionic bonding, covalent bonding, and metallic bonding. Now, ionic bonding is the electrostatic force that holds oppositely charged particles together. Okay, so that's the definition of ionic bond, but what I'm going to do is kind of take you through it and show you what's actually going on. Now, most of today's video is going to be over ionic bonding, but I wanted to go ahead and give you the definitions of all three so that you could compare and contrast. So a covalent bond is one that results from the sharing of valence electrons. So in ionic bonding, we're going to have oppositely charged particles sticking together. Covalent bond is when two atoms are going to share electrons together. And then we have metallic bonding. And metallic bonding is the attraction of a metallic cation for delocalized electrons. So remember that a cation has that T in it, which means plus sign. So a cation is a positively charged atom, in this case a metal, okay, for delocalized electrons. And like I said, in this first video, we're going to be focusing on ionic bonding, and I'm going to tell you all of the base information for that, and then we'll come together to do some practice for it. But what you need to know is that electrons are what form chemical bonds. What those electrons do determine the type of bond that those atoms are going to form. So I'm going to tell you what those electrons are doing in an ionic bond. So, what are those electrons doing? In an ionic bond, the electrons are going to be transferred from one atom to another. One's just going to give it away because it would rather do that, like we talked about in our last unit, and the other atom wants to take it. It wants to get that 8, and it's so close. So we have one atom that wants to give its electron away, and another atom that wants to take it. Okay? The atoms that would rather give away electrons are those atoms that have less than 4 valence electrons. And I will explain to you why. So let's take a look at our periodic table right here. Let's review how we know valence electrons, which we know that we have group 1 right here, and that its outer energy level is 3s1, which means that they only have 1 electron in that outer energy level, so 1 valence electron. This group has 2. Okay, we've gone over this a few times. 3, 4, 5, 6, 7, and 8 valence electrons. Okay, so that's how we know. Depending on what group they're in, we know how many valence electrons that they have. Those groups that would rather give them away, I just wrote it on my blackboard, are those groups that have less than 4 valence electrons. So if we go through this periodic table, those groups that want to give away electrons are this group, and this group. They are more than happy to give those electrons away because they would rather give away those few than try to gain many, many more to get to that magic number of 8. Okay? So an example that I'm going to take from the periodic table we just looked at, it is in group 1, so it's one of those that would rather lose electrons than gain it, and I'll show you why. It is sodium. Okay? And sodium has, a neutral atom of sodium has 11 protons, which are positively charged, and it has 11 electrons, which are negatively charged. Okay, so to show you kind of what's going on with this atom, redo my picture here, I'm going to draw sodium down here. And in its first ring, we always have 2 electrons, so I'll go ahead and draw those. Second ring, we're going to have 8. Okay, but now we only have a total of 10, so we know we have to go to that third ring, and it's got that one sitting out there. So why does this atom want to give away that 1 electron? Well, take a look at it. It could either gain 7 in this outer energy level to get to 8, or it could just say, okay, you can have this one. And then this inner shell right here is already full. So it says, go ahead, take it. But when we do that, we're down to 10 electrons, which gives us an imbalance of charges. So instead of being neutral, this atom is now positively charged because we have more protons than electrons. So now we've solved one half of this puzzle. We've got our 1 charged atom. Now we need to figure out how we get the other one. So let's go back to our periodic table. So now that positively charged atom is going to bond with one that wants to take electrons. Those atoms that want to take electrons are those atoms that have greater than 4 valence electrons. So we're looking for those atoms right there, the ones that have more than 4. So if I go back and write my valence electrons on this periodic table, we're going to find those atoms with more than 4 valence electrons on the right-hand side. Okay? So we're talking about this group, and this group. Not the noble gases, because remember, they already have that perfect number of 8. They don't want to do anything. But these atoms in these green columns right here, they want to grab some electrons. So they're kind of the other half of the puzzle. So an example of an atom that would like to gain, write that up here. We're going to go with something on that right-hand side off my periodic table, and you'll find that fluorine is there. And it has 9 protons in a neutral atom and 9 electrons. So what's going on with this is that we've got our 2 electrons on that inner shell, and then it's got 7 more in this second one, for a total of 9. But remember that magic number in that outer energy level, this level right here, is 8. Fluorine has 7, so it's so close. It just needs 1 more electron to get there. So what's going to happen is that electron from sodium that was in that outer energy level from earlier, and we want to get rid of it, well, it can just go right here, giving fluorine 8, making it stable because it has that perfect number, but it adds to our electron count. So now we have 10. So now fluorine has a negative charge. So now we can make our bond because we have our oppositely charged atoms. So I've kind of redrawn the situation for you. I've got my sodium atom and my fluorine atom, and we said sodium wants to give this electron away so it can get to that inner ring that's full. So this electron wants to go, and fluorine wants to take it. So that is our transfer that we talked about in the definition. It's going to transfer electrons. So that electron lands right there, giving sodium a positive charge, fluorine a negative charge, and look at that. We've got oppositely charged atoms. Opposites attract, guys, just like magnets. Positive charges attract negative ones. So this right here causes an attraction. And that is the electrostatic force they're talking about, that attraction right there. So opposites attract, you get that electrostatic force, they form a compound that we shorten like this. NaF, which stands for sodium fluoride. And that is how an ionic bond takes place. I'm going to give you one more example before we finish up, and that is with beryllium, which has 4 electrons, so 2 in the inner shell, because that's all it can go there, and then 2 more. Beryllium's on the left-hand side of the table, wants to give away electrons. We already know that. So the question is, how is it going to bond with fluorine, which we know has these 2 and these 7? Well, seems pretty simple, doesn't it? Beryllium wants to get rid of them, fluorine wants to take them. So one of them just goes right in there. So now fluorine is negatively charged, but beryllium didn't get rid of both of these. It still has 1 in the outer shell, so beryllium's still not happy. So what happens is, instead of bonding with one fluorine atom, beryllium just finds another one, or fluorine finds beryllium, and takes that other electron off his hands. So now, that fluorine is negatively charged. Our beryllium has a 2+ charge, and you see how beryllium balances this out, a 2+, and then we have 2 minuses here. So the compound this time is BeF2, or beryllium fluoride. Okay? So our next question is, what sort of properties do these compounds have? Alright, so some properties of ionic compounds. The first one is that they form a crystal lattice, which it's best to just show you a picture of this. This is a crystal lattice. Okay, and all that means is that they form these regular shapes because the atoms within the compound have a regular arrangement. You see how there's kind of a pattern going on in there? The other properties are that they have high melting and boiling points, and they are very hard, brittle solids. And those properties tell me that an ionic bond is extremely strong. To kind of finish out this video, I'm going to tell you the types of elements involved in an ionic bond, and this will help you identify an ionic bond every single time. So here's the way that I see it. An ionic bond always happens between a metal and a nonmetal. The metal are the atoms that want to give away their electrons. They're on the left side of the table, so that's a given. Metal and a nonmetal, which means a positive ion is with a negative ion. Another word for that is a cation bonding with an anion. So those are the types of elements involved. So that's not 3 different types. That's 3 different ways of saying the same thing. Metal and a nonmetal is the same as a positive ion and a negative ion. Metal and a nonmetal is the same as a cation plus an anion. Alright guys, that's the end of your first video for your chemical bonding unit. I hope it was helpful, and we'll come back and talk about some of this stuff here pretty soon.